The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell gonna raise a little hell, metaphorically that is. Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm your host, Desiree Shell. Today we'll be talking about volcanoes, their causes, and their sometimes unexpected effects. A little later I'll speak to Jacob Lowenstern, scientist in charge at the Yellowstone Volcano Observatory. But first, let's sit down with Nick Klingaman, a research scientist at the University of Reading in England. His research focuses on tropical climate variability and change. From 2009 until 2012, he worked with the Queensland government in Australia to help them understand how climate change would influence the state's rainfall. He is the co-author of The Year Without Summer, 1816, and The Volcano That Darkened the World and Changed History. Welcome to the show, Nick.
Thank you.
Now, your book actually begins in 1815 in Sumbawa, so maybe give us a sense of what it was like there.
There had been some minor tremors coming from the volcano from Tambora for a few months or so before the major eruption. But largely things were fairly peaceful after the British had taken over possession of the territory from the Dutch. There was a small community of native Indonesians living there on the island. And they largely thought that the volcano was extinct, that it was dormant. And so they really didn't think apparently very much of these minor tremors before the main eruption.
And what was the climate like?
So we'd just come out of a period called the Little Ice Age, which was a particularly cool period for recent history. The world was starting to warm up a little bit after that, but Sumbawa in Indonesia experiences, mainly a tropical climate, of course, and being very close to the equator, there's not much variation in the seasons. One day is pretty much the same as the next. It's probably about 90 degrees during the day and 70 or so degrees Fahrenheit at night. And then it usually rains about 4 or 5 o'clock every afternoon. In the islands of Indonesia and around that whole area, they get very regular storm activity every afternoon because that buildup of heat and energy in the atmosphere.
All right, so you say that there was a volcano, but they thought that it was inactive. What gave them that impression? Just it didn't do anything?
Well, it hadn't erupted for a few thousand years, really. There is no typical pattern for a volcano. You might have periods of dormancy, like, a few thousand years, like we had with Tambora, or you might have, more regular eruptions once every 100 years or once every 50 years or so. And what happened in April of 1815 was that we saw one of the 4 strongest volcanic eruptions of the last 10,000 years anywhere on the planet. So there were, as I said, these few minor tremors. Then there was an initial eruption about 5 or 10 days or so before the main blast went off. The major eruption, the one that was one of the 4 strongest of the 10,000 years, went on for about a day and a half. It was so strong and it put so much material up into the atmosphere that the ash cloud, after about 24 hours, the ash cloud was roughly the size of Australia. It's a massive eruption. This ash cloud is spreading out into the air, and then the slow, steady rain of ash coming down from the air and reaching the ground, and it poisoned a lot of crops actually, and that's how most people died. Not from the eruption itself, not from the lava flows, but from the fact that it just killed everything for hundreds of miles around with this poisonous ash and acid rain.
Well, maybe for anybody who hasn't been in a volcano eruption or hasn't actually seen one happen, I guess what would it look like? What would it feel like?
You would have seen, of course, the massive plume of ash and smoke going up into the air. You wouldn't have been able to make out much of the volcano at all, no matter how far away you were standing from it. I mean, whether you were inside the kind of ash cloud or outside of it, simply because the mass of material and is obscuring the volcano. There would have been loud bangs, and in fact, the governor of the island, the British governor who was there, Sir Thomas Stamford Raffles, who later went on to be governor of Singapore, he thought that the eruptions were a cannon fire. And so he actually sent troops out in boats because he thought, maybe someone was trying to invade. And yes, you would have heard these loud bangs coming from the volcano and this huge plume of ash and smoke coming out around it. And there were some minor earthquakes as well. Some minor tremors created too from the lava flows running down. And when they hit the water, they would cause these explosions as well from that hot lava meeting the cold water.
The people who did not die during the eruption, how long did it take for the rest of the island to hit bottom, as it were?
I would imagine within a couple of months, you would have seen most of the deaths simply because, there wouldn't have been any food. People wouldn't have stored food, and there's no refrigeration technology, of course, nothing, no way to store food much in the same way as we do today. Within a few months, it would have been devastating there. And there are also outbreaks of disease as well, and, simply because of, with the malnutrition and everything. It was quite a catastrophic situation for those islands. The volcanic ash plume, it actually reached far above the levels where, most of our weather happens. So most of our weather takes place in what we call the troposphere, which is the lower, say, 15 kilometers or so, which is about 10 miles of the atmosphere. But the plume was considerably higher than that, so it reached up about 18 miles high. And in doing so, it reached up into the stratosphere. Now, the stratosphere is a very dry place because there are no clouds to reach that high. Once the plume gets up there and once the ash gets put into the stratosphere, it's not going to quickly fall out. And that happens simply because if you put material down into the troposphere, down where most of our weather happens, then eventually it'll rain. It'll literally rain out of the atmosphere because water droplets will condense onto these ash particles. But once you put all that material up into the stratosphere, well, there are no clouds up there. There's no weather activity, and so the ash stays up there for quite a long time, and it starts to spread out all over the globe due to the very strong winds in the stratosphere. And so this very thin, imperceptible cloud expands all over the globe and starts to reflect a small portion of the sunlight.
You're listening to Skeptically Speaking, and I'm here with Nick Klingaman, co-author of The Year Without Summer, 1816, and the volcano that darkened the world and changed history. Okay, so let's get specific. The volcano eruption, what kind of weather patterns did it cause? And where?
So predominantly the effect is to cool the entire planet. It does that on average by about 3 degrees Fahrenheit. But because it cooled the planet unevenly, it cooled more in the tropics than it did, in the equatorial regions than it did in the higher latitudes up in the Arctic. It starts to change the jet stream. And so the jet stream you can think of as a conveyor belt for weather systems, for the low pressure systems that bring us unsettled weather. It changed the jet stream and the way that jet stream flows across the Atlantic. And so it began to bring very unsettled weather to Europe, very cold, very damp weather in the summer of 1816, with just this progression of rainstorms, of cyclones barreling into, say, France and Switzerland and the United Kingdom, and just produced this terrible conditions there. But also started to allow very cold air from the Arctic, from Arctic Canada, down over the eastern United States, and actually produced snowstorms in June of 1816 in southern Canada, in Quebec and Ontario, down into New England. Some places received nearly a foot of snow. What happened was that because the tropics cooled more than the Arctic, the strength of that jet stream and the degree to which it's oriented west to east instead of north to south is controlled by that temperature difference between the equatorial regions and the higher latitudes. And so when that temperature difference is weaker, the jet stream itself becomes weaker, so those winds high up in the atmosphere, that conveyor belt weakens, and it starts to meander. Instead of flowing kind of due west to east around, it starts to meander to the north and to the south. That allows these very large changes in the air masses to take place. So where it dips to the south over southern Canada and the eastern United States, you get this cold air draining down from the Arctic. And then where it bows up to the north, as it started to do over central parts of Europe, you get this flow of very moist air off the Atlantic Ocean that brings these rainstorms and the very wet, unsettled conditions that we saw in those regions.
Now, we know this now. But they did not know this then.
Of course, the science of meteorology, the science of understanding the weather and the climate was just in its infancy in that time. And there were some rudimentary weather instruments. People had basic thermometers and barometers, but they had no way to predict the weather in the same way that we do today. They blamed all kinds of things for the disruption. Most people blamed God, first and foremost. A lot of other people blamed earthquakes, or they blamed changes in the Earth's magnetic field. Some people pointed to sunspot activity. We'd just come out of a period during the Little Ice Age of very, very low sunspot activity, so people weren't used to seeing them. And around this time, we saw there were some very prominent sunspots appearing on the face of the sun, and people just made that link. It's the old adage about correlation not being the same as causation, but people then, they're just looking for anything to grasp onto to explain what's happening to their weather patterns.
Did anyone actually think it was the volcano?
No. So the volcano, the eruption wasn't reported outside of the local area there in Indonesia. Most people in Europe and the United States would have had no idea that there had been this massive eruption, and so they simply couldn't have made that link, and they didn't have the scientific knowledge to make that link either.
Well, now, especially in 1816, people's lives and their livelihoods were very dependent on the weather, correct?
Yes, so particularly with agriculture, and most people are still, subsistence farmers. They're trying to grow what they need to survive on their own little plots of land. And so this was simply devastating, where we had not only the very cold weather, but in the United States we experienced a lot of very dry weather during the summer and autumn of 1816. And then in Europe they had this persistent rain and this persistent flooding that just ruined the crops there.
Well, and it seems to have been particularly intense in Ireland.
Yes, and Ireland being so close to the sea as well, again with this procession of unsettled weather, these storms coming off the Atlantic Ocean and affecting Europe, made conditions absolutely brutal in Ireland and caused actually a massive epidemic of typhoid there, which killed tens of thousands of people. I think 60 or 70,000 or so in the end died in the epidemic of 1816 and 1817.
Well, so maybe let's talk about some of those things that happened due to this weather. Crops were definitely affected.
Yes, so most of the crops just simply couldn't have dealt with either the drought on the American side of the Atlantic or the flooding rains in Europe. But also there was a problem with the way that the governments responded, primarily in Europe, actually, because the governments were very reluctant to offer assistance to the poor in that time. There wasn't the same system of welfare, government assistance for the poor that there is today. And so people were simply starving and being forced out of their homes due to the flooding rains and due to the lack of food. And we found evidence of these wandering bands of vagabonds, basically roaming from town to town, looking for charity, looking for some kind of assistance, and finding really little of anything to eat, assistance from either the governments or from private individuals.
This was a really interesting part of the book because you used so many people's personal stories and diaries throughout it. How did you find those?
So we're fortunate that a lot of diaries have been archived in libraries. So I spent quite a bit of time in the British Library looking at diaries of prominent figures from the time, like Sir Robert Peel, who was then the Governor General of Ireland and was later British Prime Minister. And so he kept very detailed records of what was reported to him about the conditions there. And then also just, prominent figures from culture and from art as well. So Byron and Shelley, who were active at the time, and Mary Shelley, his wife, who later went on to write Frankenstein, based on the events in 1816.
They wrote a lot about the rain during that period of time.
Yeah, so sometimes the diaries can be quite boring, actually, because you're just going through and reading, today it was very wet and cold and, there's nothing to eat. And tomorrow, you get onto the entry for the next day, still very wet, still very cold, still pretty much nothing to eat.
That's awful.
It's terrible, but these were the experiences of people at the time, that such a shortage of food in many areas. The governments were actually trying to suppress news of the poor harvests, the crop failures, simply because they didn't want another public uprising. They'd learned the lessons of the French Revolution.
Right.
That, you don't want this kind of unrest to be able to take hold. And so they were trying as much as possible to suppress in the newspapers any reports that this bad weather was going to cause the crops to fail.
And it was open propaganda at that point. Like the media was not reporting on the same things that people were actually seeing in their day-to-day lives.
No, there wasn't the same concept, I guess, of a free and open press the way that there is today. The governments were telling the newspaper editors what to write.
Well, and there were mass emigrations at that point as well.
So in the United States, we saw a lot of westward movement of people. So farmers who were convinced that the local weather patterns had turned against them. You have people in New England, say, who thought that the bad weather was caused by deforestation. So they'd come through and they just completely clear cut all these old hardwood forests to make their farms, to build their homesteads. And they were sure that these weather patterns were due to the fact that they'd cut down all the trees and replaced them with crops. So they packed up and they moved west into the Ohio Valley, say, and out towards the Missouri territories.
Well, and so were some of the ideas for discounting the fact that no one thought it was a volcano, a lot of their thoughts around why the Earth would warm or cool, some of that was actually correct.
They had some theories which proved to be true, or at least not completely false in the end. But it wasn't due so much to a scientific understanding necessarily as almost random guesswork. So they were blaming anything and everything that they could get their hands on, really.
This is Skeptically Speaking, and I've been talking with Nick Klingaman about his book, The Year Without Summer. And we'll be back with more after the break.
Skeptically Speaking is rebroadcast on a number of fine radio stations. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
Welcome back to Skeptically Speaking. I'm your host, Desiree Schell, and I'm joined by Nick Klingaman, a research scientist at the University of Reading in England. He's the co-author of The Year Without Summer, 1816 and the Volcano Which Darkened the World and Changed History. Now, we were talking about that no one recognized that the weather changed because of the volcano. So did they not have an understanding of how the weather worked at all at that point, or was it the technology, or what was the issue?
There was some basic understanding of the changes, say, that were due to the seasons. Many people used what we today would call an analog technique for trying to predict what was going to happen to the weather, say, a month or so down the line. And that's simply based on what does the weather look like today, and what have the changes looked like over the last few weeks, and how can I match that up with something in my memory, something in my past experience? So the weather over the last few weeks has seemed a lot like the weather of 10 years ago. So I'm going to predict that what's going to happen over the next month will be a lot like what happened in that month subsequently 10 years ago. So they're just trying to use that kind of pattern matching, what we meteorologists today would call an analog technique for forecasting. But by and large, they had no ability to predict the weather like we do today using computers and lots of very detailed observations that we make, simply because while there were people making weather observations, while they did have some instruments, they weren't sharing that data. They couldn't communicate it fast enough to make a forecast in the way that we make them today. We use very powerful supercomputers to make weather forecasts today. Weather forecasting is actually the second largest use of supercomputing time in the world, second only to modeling nuclear eruptions, nuclear bomb blasts. So we use these very powerful computers, and we're constantly monitoring weather conditions all over the globe. And that information gets fed into very detailed computer models, which are based on the laws of physics, which take that information and then model how the atmosphere is going to evolve over the next few days and weeks.
Well, since a lot of your book is actually based on sort of the economic impact that these changing weather conditions had, would you say that we're equally dependent on understanding where the weather is going now?
Of course. I mean, weather forecasting is hugely important to so many aspects of the economy. We need to have the most accurate and detailed forecasts that we can, not just for the weather forecast that you'll see on the Weather Channel or on your local news for the next 7 days, but weeks and months ahead. We do actually make and issue forecasts these days for weeks and months and seasons ahead. We just know that they're not as accurate as the ones, for tomorrow. That people use those when, for instance, farmers will use those in deciding when to plant and harvest their crops.
Well, now, when did the weather start to get back to normal? Back to 1816?
The conditions returned to normal around about 1818 or 1819. So 1816 was obviously a very cold year because of the effects of the volcanic eruption. 1817 was moderately cold. It wasn't quite as cold as 1816, but some of that sulfuric acid cloud that was high up in the stratosphere was starting to be pulled down. There is the occasional cloud that makes it high up into the stratosphere, and that was starting to slowly rain out some of those particles. Yeah, so 1817 was a moderately cold year. 1818 was a little on the cold side, and by 1819 we were pretty much back to normal.
But this did do some serious damage to the people that lived in those areas. So how long did it take for that to get back to normal?
The economic consequences certainly stretched on for a few years after the eruption. It took farmers a while to be able to, the ones who had migrated west, they've got to go out and set up their new homesteads out there, set up their new farms. For many in Europe, cleaning up the aftermath of the flooding took probably the better part of a decade, really. And the poor conditions that we saw in Ireland with that typhoid epidemic and so many people forced into abject poverty because of the conditions began a cycle of disease and economic ruin in Ireland that stretched all the way up through the Great Potato Famine in 1845-46.
Could any of this been prevented? At least could some of the damage have been lessened in any way?
It's possible that some of the damage could have been lessened if governments had been a bit more willing to step up to the plate and provide financial assistance or to release more food stores. We found that generally those regions, so there were some regions in Germany and some in Poland where the local governments provided much more to the people in the way of charity, and those populations generally fared considerably better than the other provinces. Even in Germany, there was no Germany at the time; it was all separate states. But other provinces in Germany where the governments were much more reticent, and in Switzerland too, they were generally unwilling to give any assistance to the poor. And in those regions, it was simply devastating to the populations and to the economies.
So what about the technology? If they were able to receive warning beforehand about a volcano, what do you think would have changed?
Nothing, at the time, simply because they wouldn't have had the meteorological understanding to have linked the volcano to the cooling and to the changing weather patterns. If something similar were to happen today and we were to have the same kind of warnings, then we could prepare for it much better by storing more food and by getting assistance out there to people much more quickly. And of course, we have the technology to do that today, as we've seen in the responses, say, to Hurricane Katrina and to Superstorm Sandy. Now we're much more able to get direct help to the people when they need it.
Well, I'm just wondering, do we as, I guess, developed nations, do we use that technology to help the nations that maybe don't have that technology yet?
We do share much of the output of our weather forecasts with nations around the world. There are international agreements that allow us to do that. And so we do provide this information to people, say, in Africa and in Southeast Asia and in other lesser developed regions. Often the trouble is that we can't give them the precise information in the precise way that they need it. There's often a disconnect between scientists and the people who use scientific information.
You don't say.
Well, yeah, and it's not so much that we don't want to give them the information that they want. It's sometimes the problem is that we don't understand what they want, and so the problem of communication comes from that end. And sometimes the problem is that we simply can't predict the things that they want to know, or feel that we can't predict them reliably enough to be able to give them an honest answer. And so sometimes, for instance, we work with people in Africa, with farmers in Africa who say, I want to know exactly when the monsoon rains are going to start and if they're going to fail at some point during the next 3 months in the season. I want to know precisely when so that I can make the most and plan the crops. And you say, well, you're asking me to give you a weather forecast for 3 months down the line. And simply not something that I can do. We can speak in probabilities, maybe, but we can't speak in certainties.
Nick, thank you very much for being here. It was a pleasure.
Thank you very much. I enjoyed it.
You can find a link to Nick Klingaman and his book, The Year Without Summer, on our website at skepticallyspeaking.com. My next guest is Jacob Lowenstern, a geologist at the U.S. Geological Survey, who specializes in the relationship between magma and geothermal activity at the Earth's surface. He acts as scientist in charge of the Yellowstone Volcano Observatory, a job that he's filled for 10 years. His work in volcanology has brought him around the world to work in places ranging from Northeast Africa to the Caucasus, Chile, and Japan. Great to have you here, Jake.
Nice to be here.
So I definitely want to talk about volcanoes, but let's talk a bit about Yellowstone as a whole. The volcano is not the only geologic hazard.
It's an active tectonic region in general, and there are a lot of earthquakes. It's at the very edge of the basin and range area of the western U.S., So there's the Hebgen Lake Fault Zone had a big earthquake in 1959, magnitude 7.5. We also have explosions out of the hydrothermal system, the hot water system that fuels Yellowstone's geysers. And some of those are small explosions, and some of them in the past 10,000 years have been relatively large.
What are hydrothermal explosions exactly?
At Yellowstone, you have the groundwater that's been heated up to boiling temperature, and it's actually boiling pretty much all the way down from the surface. It gets hotter and hotter as the pressures increase. So you have a column of boiling water, and that boiling water is unstable. And if for some reason the pressure decreases, that means that you have a lot of water that's above its boiling temperature and will rapidly and violently flash to steam and throw rocks out of the ground while it does that. It's sort of like a pressure cooker. If you release the pressure on a pressure cooker, you can get an explosion. Somewhere in the park, there's a small one almost every year. Back in the late 80s, there was one that put a hole in the ground maybe 5-10 feet across. Back in the 1880s, there were larger ones. And then if we look back in geologic history in the past few thousand years, there have been some very, very large explosions, some that created holes that are a mile or so across. So some really large features at Yellowstone caused by these non-volcanic, non-magma-related explosions.
What's the difference between a geyser and a steam explosion?
We're really just talking about two end members of something that can happen. A geyser eruption is just when water itself comes out of the ground explosively, happens periodically. Occasionally those geyser eruptions can be a little bit bigger and they can throw a few bits of rocks out, and then at the other end of the continuum you can have something where really something unexpected and large occurs, rapid flashing of water to steam and causing a lot of rock to be hurled out of the ground. So it's really just sort of a continuum from the pure water phenomenon to the water plus rock phenomenon.
So what would do something like that? What would cause it?
We don't always know. There have been a number of them in New Zealand where people have seen that there have been small earthquakes that have set them off. Yellowstone, there's some documented evidence for a draining of a lake that can reduce the pressure on a system and cause explosions. It's possible that just a really large geyser eruption could sometimes set off the rocks to explode as well and get a hydrothermal explosion. So again, we don't have that many of them at Yellowstone that are occurring where we can study them, so we don't really know what sets them off in detail, and fortunately they don't occur very often.
Well, I have to ask the obvious question at this point is about Old Faithful. So why is Old Faithful faithful, as it were?
Old Faithful, for as long as we've been watching it, has been relatively faithful. It hasn't stayed the exact same timing. It used to be more along an hour time frame. Now it erupts more around 90 minutes. But it's a fairly separate system from all the ones around and seems to have its own plumbing system that is very regular, very consistent geometry, and doesn't get affected by a whole lot of things going around outside.
Are there any other that are that regular?
There's one at the Norris Geyser Basin, for example, called Constant Geyser, which goes off more on the order of every 15 or 20 minutes, and it's very, very constant most of the time. It does shut off occasionally, but not for very long. There are some very small ones, but I could say Old Faithful is most regular large geyser eruption.
Okay, well that wasn't scary enough. So on to earthquakes. How often do you see them at Yellowstone?
Well, there's constantly earthquakes occurring at Yellowstone. We get on the order of somewhere between 1,000 and 3,000 earthquakes in a typical year. So they occur often. It's a very active area, partly because of the tectonic region, but partly because there's molten rock down there and it heats up the rocks. There's hot water that's moving around and boiling. So there's just a lot of instability in the region, and rocks break as a result and cause earthquakes.
And how powerful are they? Are big enough to do damage or to really affect the area?
Very, very few are big enough to do any damage. In fact, only typically 5 to 10 a year are felt by anybody. Most of them are too small. They're lower than a magnitude 3. Most of the ones that we're counting are down magnitude 1s, less than that even. So they're relatively small events, but if you've got a seismic network, you can detect them.
Well, the concern, of course, is, that an earthquake could somehow provoke a volcano eruption. So is that the case?
It's always out there, again, as a possibility, but if you think about the big earthquakes around the Yellowstone region and how often they occur, the Hebgen Lake Fault Zone, for example, and Tetons down south, a big fault range that's had many big earthquakes in the past few thousands of years. There have been literally hundreds of very large earthquakes, magnitude 6 and 7 and above, in the period of time since Yellowstone last erupted. In other words, there's big earthquakes happening a lot, and they don't set off Yellowstone.
Well, you've also seen earthquake swarms, which is a term that I was not familiar with.
Right. That's kind of a typical way that things happen at Yellowstone, and it's fairly common on volcanoes, fairly common in hydrothermal areas as well, with a lot of boiling water. And instead of having a big earthquake and then lots of smaller earthquakes following subsequently, instead it's a series of earthquakes that have no big versus small earthquakes. They're all relatively similar. There are smaller ones and there are larger ones, but you might have, for example, 10 magnitude 3 earthquakes. And nothing any bigger, and then lots of magnitude 2s and 1s. They also can go on for weeks sometimes. We had a swarm back in 2010. It took about a month to take place, and there were about 2,500 earthquakes in the end, so lots and lots of earthquakes. Only 10 of them maybe were felt by anybody, but lots of them were recorded by the seismic system.
Okay, so at this point we are allowed to talk about eruptions. So when was the last eruption?
The last volcanic eruption where molten rock came out of the ground was about 70,000 years ago at Yellowstone. It formed one of the plateaus within the park called the Pitchstone Plateau, big rhyolitic lava flow. Rhyolite is a composition of rock similar to granite, but it comes out on the surface. Mostly it's glass, forms obsidian, beautiful stuff. And the Pitchstone Plateau part of the park was formed by one really big, long outpouring of lava that may have lasted for years, and it occurred about 70,000 years ago. There's not very much evidence for a lot of explosive activity during that eruption. Certainly, most of these big lava flows that are common at Yellowstone have these outpourings, but don't really have a whole lot of explosive activity, don't seem to affect regions far beyond Yellowstone itself.
So when a volcano erupts, what happens exactly? For those of us who cannot possibly remember elementary science class.
They might not even teach it in elementary science class. And the first thing that happens is there's some magma down beneath the ground, molten rock, and it gets pressurized, maybe because it's crystallizing and gas is coming out and pressurizing it, maybe just because it's a lot less dense than the material around it and it wants to rise. For whatever reason, it starts rising towards the crust, the Earth's crust, the surface. Usually a lot of earthquakes occur. The magma cannot move without breaking rock on its way. So we get lots of these earthquakes, sometimes swarms of earthquakes. Usually they're going to be pretty big earthquakes, and we're going to have them in the region where the magma's rising. Get a lot of uplift of the ground. The movement of magma actually bows the earth upwards. And then at a place like Yellowstone, we'd start getting some explosions as the magma hit the hot waters and the ground waters. Start some explosions, and then eventually the material makes it to the surface of the earth, and it comes out explosively in some cases, or maybe it loses its gas before it gets to the surface, and it comes out relatively peacefully.
You make it sound so pleasant.
Well, to somebody who studies volcanoes for a living, it is. It's interesting stuff.
This is Skeptically Speaking, and I'm talking to the scientist in charge of the Yellowstone Volcano Observatory, Jacob Lowenstern. So what kind of effect does a volcano have on the geographic area around it then?
If you have a lava flow, the main problems that you can have is you're going to cover up ground surface. So if you have houses and things like that, obviously they're going to not do too well. You can also block rivers in some cases and dam up, form lakes, and that can cause eventually flooding when the dam fails or the water overtops the dam. Another thing that frequently happens with lava flows is they can start forest fires. And obviously people who remember 1988 at Yellowstone remember that there's some pretty big fires in that area. So that's another thing that could happen if there were a big lava flow at Yellowstone. There are bigger, more explosive kinds of eruptions as well. Some of those occur every year somewhere on Earth. There's some explosive eruptions. They can cause pyroclastic flows where there's lots of moving ash going through the air, destroying things. And at Yellowstone, there have been really big eruptions in the geologically distant past, and those often, those can cause big damage all around the country in some cases.
Well, let's look a little closer at this, I guess, using the recent history of Yellowstone. Let's talk about the Denali earthquake in 2002. Can you walk us through that?
Well, I just started my work at Yellowstone at that point in time. I think even that day was my first day as science in charge, and turned out that there was this big eruption up in Alaska, magnitude 7.9, oriented on a strike slip fault, and it oriented the waves coming away from that faulted region down towards the northwestern U.S. And the surface waves, there's different kinds of waves that are generated by earthquakes. The surface waves are the ones that move on the surface and not really through the center of the earth. They were tremendously large, and they caused a lot of seismic readings way down, a couple thousand miles away from the epicenter to be off scale, where you couldn't actually record the waves faithfully because there was too much ground shape. And sure enough, when those waves hit Yellowstone, they caused all sorts of local earthquakes at Yellowstone. There were many hundreds of earthquakes occurring in the next 24 hours all around the park, presumably because you had pressurized hydrothermal fluids that were getting tweaked and moved around and caused to boil and break rocks and things like that. And so it was a really unusual example of triggered seismicity, something that we recognize often when there's a big earthquake going off somewhere in the world, especially strike slip faults. But this was one of the classic examples as documented in the past 15, 20 years of triggered seismicity.
So wait, that was your first day?
Yeah, it's pretty crazy. Fortunately, I'm not a seismologist. The folks at the University of Utah who do the seismic recording, they were busy that day trying to figure out what was going on. They sorted it out. There's some nice publications that have come out of that so that we understand a little bit more about how these things work.
Can you explain the term uplift? Because it has some really interesting relationships and the things that it causes.
Yellowstone is a caldera region. That means that caldera is basically a hole in the ground that occurs after the ground caves in when you remove a lot of magma during a big eruption. And that's the kind of volcano that Yellowstone is. Since the biggest eruption at Yellowstone, or the most recent big eruption 640,000 years ago, that caldera is filled in with more recent lava flows. So when you go to Yellowstone, you don't necessarily see a big hole in the ground anymore. But that entire region, that caldera, still has magma down there. There's molten rock down there, and it pushes up on the surface of the Earth, the ground surface, and it causes it to upwarp. That phenomenon occurs every now and then the pressure subsides and the ground moves back down. And so if we look over the 50, 100-year time period, we see a whole series of uplift and subsidence cycles where the ground moves up and the ground moves down, and the ground moves up and the ground moves down. And for example, between 2004 and 2010, there was about 25 centimeters maximum of uplift of one part of the caldera. That was the maximum uplift. That's a pretty good amount for any one particular area of the ground to rise up. But in the case of Yellowstone, there's this big caldera that's about 2,500 square kilometers, and all of it was rising up. It wasn't all rising up as much, but it was rising everywhere a little bit. And so if you put that together and you figure out the volume change, there's a lot of the Earth to be moving up and down.
Indeed. So that actually causes a lot of kind of weird thermal activity, correct?
Well, it can. This is something we don't really understand that well, but we do know that there was a period between, 1998 and 2003 at the northern part of the caldera and near the Norris Geyser Basin, where there was considerable uplift during that time period, and there were a lot of changes that were noticed in the thermal areas, especially towards the end of that time. And so it does appear that if you flex the crust, if you push at it, you can get fractures to grow and you can get fractures to be created. And so you might get changes in the amount of thermal activity during those time periods. So we're still learning about that because we haven't really lived through that many of these cycles to see if every time we get uplift, we get the same sort of thermal phenomenon. But that's one of the things that we're definitely watching.
The thermal phenomenon, as it were, did some damage to some bison, I understand.
The real thing that went on is a lot of hot ground that grew hotter in several of the summers. There was also increases in the eruption rate of some of the big geysers in that part of the park, things that don't erupt every year, were erupting multiple times a year. There was an event as well where I think 5 bison were found dead on a very cold wintry night after a very cold wintry night. It's not really clear that that is directly related to the uplift, but it's certainly another interesting phenomenon that occurred, presumably because the bison were bedded down in a thermal area, and it was so cold and so windless that when they woke up, they were sleeping in the middle of all of the gas, the carbon dioxide and hydrogen sulfide, went to the lowest point, and that's where they were. It's not something that happens very often because it's usually pretty windy at Yellowstone, but on some really cold winter nights, that can happen.
So for anybody who's planning a trip to Yellowstone, are there warning signs perhaps? Could that happen to a human, is what I'm saying?
There are very few people who are going to be camped out on the coldest winter windless nights in low areas. In general, people are encouraged to go on the boardwalks and on trails, and they stay at established campsites where they're allowed to stay. And so people are generally going to be in the places where they're supposed to be, and those places are safe.
This is Skeptically Speaking, and we'll be right back to talk some more about the volcano in Yellowstone Park with geologist Jacob Lowenstern after these messages.
On the next episode of Skeptically Speaking, we look to the stars that light up the night sky and fuse hydrogen and helium into the elements that make life possible. Science writer Jennifer Willett examines the possible evidence of ancient supernovae in bacterial fossils. Astrophysicist Ethan Siegel explains the controversy surrounding the so-called black hole firewall paradox. And astronomers Pamela Gay and Nicole Gallucci of CosmoQuest discuss the impact of U.S. sequester budget cuts on their research and outreach. That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
Welcome back to Skeptically Speaking. I'm your host, Desiree Schell, and I've been talking about the signs of volcanoes, or one volcano in particular, with Jacob Lowenstern, scientist in charge of the Yellowstone Volcano Observatory. So what's going on with Yellowstone now? There are very literally a ton of different ways that researchers are monitoring activity, correct?
The primary way that we monitor Yellowstone is through seismic network. We have over 30 seismic stations around the park, and they send data real time out to the scientists and to the public. Everybody can look at the data, and we watch with time. So in general, the last few years have been relatively slow. There haven't been too many earthquakes. The last big swarm of earthquakes is in 2010. But we do get little swarms every now and then. There's some sort of earthquake occurring almost every day in the region. Another thing that we do is we have GPS receivers around the park. These are similar to what you might have in your car or carry out on a hike, but they're attached to a monument, and they can give very, very precise information on exactly where they're connected to the Earth. So giving information with sorts of sub-centimeter levels of accuracy down to a millimeter in terms of where they are in terms of the latitude, longitude, and elevation. So we look at that data, we have that information, we can see when different places in the park are rising or falling. Yellowstone, since 2010, also has been generally subsiding several centimeters. It's been dropping down. Prior to that, it had been rising.
When was the last time that you did see a greater than usual amount of activity?
Definitely in very end of 2008 and early 2009, we had a big swarm under Yellowstone Lake. About a year after that, 2010, we had a big swarm of earthquakes out on the Madison Plateau. So those were two pretty anomalous seismic swarms, lots of earthquakes. They were also occurring at a time when we still did have some uplift of the caldera. The system was pressurizing. For whatever reasons, it was pressurizing, but it was pressurizing. And then after those big swarms, we've noticed that things have started subsiding again.
So then what would the signs of impending catastrophe be exactly?
It's important to realize that there can be another volcanic eruption at Yellowstone, but about the last 80 eruptions at Yellowstone have not been impending doom, that's going to have a big effect on the entire population of the United States or Canada. So any kind of volcanic eruption we're going to see, if we do see one, we're going to have a lot more earthquakes, a lot more than typically happen in these swarms. They're going to be bigger. We're probably going to get magnitudes 4s and 5s. Yellowstone hasn't erupted in a long time, so you got to break a lot of rock if you want magma to come out of the ground. And breaking a lot of rock requires a lot of big earthquakes. then again, you're going to see explosions because you can't rise magma towards the surface of the Earth without intercepting this hot aquifer, this hot groundwater system. And so you're going to flash that water to steam. You're going to cause explosions. So we're going to get that, and we'll probably get a lot of ground deformation as well. Much, much more, order of magnitude more than we typically see during these caldera uplift and subsidence cycles. And then finally, we're going to see more magmatic gases. We'll probably see some sulfur dioxide before we actually get an eruption, and that would be generally a telltale signal that magma is close to the surface when we get that kind of gas, as opposed to the carbon dioxide and H2S that we normally see. So those are the kinds of things we'd expect. We see them all in very low abundance, and at this time, they're the kinds of things that Yellowstone is always doing, having these earthquakes. But we're going to see more of them, bigger, happening all at the same time, causing some explosions. Even if all that were to happen, it still doesn't mean that we're going to have a big eruption, because all of that would have to happen even for a relatively small eruption.
Okay, then worst comes to worst. All the red flags go up. Every base is covered. What is the plan? What's the next step?
Well, the next step would be that those who are in charge of the land managers, the police officials, the governors of the states have to make decisions on what is the safest thing to do for the people who are living around there. In general, again, if we're going to have a lava flow, there doesn't really need to be a whole lot of movement of anybody. But if we knew that there was going to be a really large eruption, it would be definitely a difficult thing to plan for. There's no way around that. If you're going to have a big eruption anywhere on Earth that puts out cubic miles of rocks, many cubic miles of rocks, cubic kilometers of rocks, then you have a problem, because your people live near volcanoes, and even if there's an eruption around the world, it's going to have effects. If you have a truly enormous eruption, for example, the Pinatubo eruption in 1991 in the Philippines, put enough sulfur and aerosols into the atmosphere that it was able to decrease the global temperature for a couple of years. And certainly the year without a summer in 1816 was a global event due to the eruption of Canberra in Indonesia. So you get a big enough eruption, and you can cause far-field effects in terms of the temperature of the Earth. And if it's a big enough eruption and it puts out enough ash, it could even impact agriculture globally. And certainly it would impact transportation of goods, of people, airplanes, ships, those sorts of things.
Not so pleasant now, are you?
Well, no, it's that's the worst case scenario, and the worst case scenario doesn't happen often, and doesn't maybe happen within a human lifetime sort of perspective, but it can happen. It does happen geologically, and if people are around on Earth for thousands of more years, well, they're gonna run into one of these.
But again, Yellowstone is unlikely to erupt anytime soon.
Yeah, certainly. Again, the sorts of things that we see at Yellowstone are the ones that we've been seeing for the last 100 years. We expect that people will be able to go to Yellowstone for hundreds and thousands of years and still see the amazing things that it offers.
Jake, thanks very much for coming.
You're very welcome.
You can find a link to Jacob Lowenstern and the Yellowstone Volcano Observatory at the link on our website at skepticallyspeaking.com.
If you're still not absolutely convinced that volcanoes are both fascinating and terrifying, we have one more interview for you. I'm joined by Robert Dahl, paleoecologist and senior research fellow in the Environmental Science Institute at the University of Texas at Austin. Lovely to have you here, Robert.
It's my pleasure to be here, Rochelle.
Now, you believe you figured out exactly how the dust veil of 536 AD went down. First off, before we go into that, what is a dust veil?
A dust veil is a phenomenon that occurs when large volcanic eruptions, explosive volcanic eruptions, occur on the planet. When I say large, I'm talking about above about a 6 on the Volcanic Explosivity Index, the VEI index. And these large eruptions typically emit not only volcanic ash, so tougher particles that are quite small, but also sulfur dioxide that eventually forms into sulfate. These items spread around the planet's outer atmosphere. They get up into the stratosphere and create basically a hazy atmosphere that the sun's rays cannot penetrate so well.
So when we're talking about a 6 on the scale, how far does the scale go? Is it like a 6 out of 10, 6 out of 7?
I think officially the scale goes up to 9, but no 9s have ever been recorded. VEI 8 are the largest super volcanic eruptions that we know of, and none of this size have occurred since about 75,000 years ago or so.
So 6 is pretty big.
6 is pretty big, and 7 is quite big.
So what kind of effects does this dust veil have?
The dust veil serves as basically, in one sense, it's kind of insulation. It causes winters to be slightly warmer. The opposite side of that is that summers can be quite cold, and the reason for that is that the solar radiation that's reaching the Earth's atmosphere doesn't make its way to the Earth's surface at the same rate that it would if there were no dust veil. So a higher percentage of the incoming solar radiation is reflected when one of these volcanic dust veils is present.
Let's get back to your research specifically. What do you think caused this dust veil?
For a long time, I didn't know. Just like the rest of the scientific community, I had thought about it a bit, but not really pursued it because it was beyond the purview of my research, really, until I started to have some questions about the dating of the Ilopango eruption in El Salvador, this event that I've worked on for more than a decade now. A number of things happened since I started working on the Ilopango eruption in the late 90s that led me to believe that this might have been the cause of the mystery dust veil that began to encircle the Earth at the end of the year 535 and really became more pronounced in 536 and 537. So when I started to realize that the dating of our eruption was going to be closer to the actual historically documented event, I decided to go back into the field, collect more samples, and test this hypothesis.
How did you come to the conclusion that you did? First, can you tell us sort of what your conclusion was?
First of all, I should say that in science we always like to leave. Well, I like to leave the door a little bit open for further interpretation and revision. But I feel very confident that we have by far the best candidate for the cause of the AD 536 event. So I'm not calling it a slam dunk or a 100% smoking gun. But what we have is we have three factors that are quite important here. One is we know that the mystery dust veil of 536 was caused by a tropical volcanic eruption. Ilopango in El Salvador is a tropical location. Number two, the eruption had to be quite large on the scale of the Mount Tambora eruption in 1815, somewhere in that range, just about a VEI 7. And we now know that Ilopango was about that size. And the third thing is we need to have an event that occurred in the early 6th century AD, or of the Common Era. And that also now, we know, fits the bill with Ilopango. So there are no other eruptions that are documented on the planet that are tropical, that are of the size necessary to cause this sort of dust veil, and that are of the age that we know would be consistent with a early 6th century eruption. So we're basically the last one standing as far as I can tell.
So I understand that there's actually a tree in El Salvador that somewhat plays a role here, isn't there?
Yeah, there are a couple of trees actually, and one is potentially more pivotal. What we had to do in this case, the reason we've been unsure about the precise dating is because the dates that are produced by wood samples from of material that was killed by the Ilopango eruption are all very consistent, and they cluster quite closely around about 1,600 years ago, radiocarbon years ago. But what has kind of been our biggest hurdle up until now is the fact that the radiocarbon correction curve is not the problem. The radiocarbon correction curve on this time period is that we have about 120, 130 year time period where 1,600 years radiocarbon years before present is equal to anything from on the calendar from about 410 of the Common Era to about 540 or 545 or so. And that's the problem. So So even though we have tight clustering of radiocarbon years, those don't precisely correlate with calendar years. So we've had to do a lot of tricky manipulations to understand the radiocarbon plateau that we're sitting on, which is every paleoecologist nightmare or archaeologist. If you're on a flat part of the radiocarbon correction curve, which we are, sometimes you can't narrow down the date using radiocarbon very precisely. But we're using a special technique. It's not that special and it's not that novel necessarily, but it's often costly because instead of dating a sample one time, you need to date a sample that has known growth increments. So these could be in succession. So these could be, let's say, a peat bog. It could be coral samples, successive years in corals, or in this case, successive growth increments in trees. So we're looking at a whole series of radiocarbon dates rather than single dates averaged together with a weighted mean, which is often what's done.
So this huge volcano goes off in El Salvador, and I think you said 535. It creates this dust veil.
Yep.
What is it like for the people living in the world at that time? Is there a noticeable effect?
Yeah, there's a noticeable effect on several different scales. I mean, first of all, everyone in El Salvador was affected. What we know about El Salvador in terms of its population density is also important. El Salvador is the most densely populated country in the mainland Americas today. It was also the most densely populated country in the mainland Americas when Europeans arrived, around 1500. So we're talking about quite a few people, many hundreds of thousands in El Salvador at the time of the eruption. We figure that the people right around the area of the greatest devastation, the pyroclastic flows, numbered at least 50,000 or so, and perhaps double that number. So those people all would have been killed instantly had they not been scared off earlier before the eruption began. But there's a much wider area, about 20,000 square kilometers, where we estimate that 10 to 20 or so people per square kilometer were living in El Salvador. So if you do that math, you're looking at 200 to 400,000 refugees. So right away, we see that there's an area of complete devastation. Everyone is killed, and about 2,000 square kilometers. Beyond that, you've got an area where you have hundreds of thousands of evacuees or refugees, many of whom do not make it out of the area of devastation because as they're walking out, there's no food, there's no clean water. They're inhaling volcanic ash that has a very high silica content, glass. So many of those people succumbed, I'm sure, to the hardships of getting out of the area and perished as they were making their way out. So that's just in El Salvador and surrounding areas of Guatemala and Honduras, where the ash was maybe a meter deep or more. You get beyond that area into the wider Maya area, and we know there were major disruptions as well. There were disruptions in trading networks. There were clear signs that during this time, a major perturbation happened in the Maya region and shifting political alliances, shifting economic relationships. There's something known as the Maya hiatus that begins in about 534 AD and lasts for about a half of a century, for about 50 years. So during that period, there was a major disruption in the Maya area, and it changed the cultural trajectory of the Maya. The largest prehistoric city in the Americas, Teotihuacan, fell around 550 or a little before, was burned down. Clearly, I'm not saying it was burned down by the eruption, but there was enough political destabilization, and Teotihuacan, the city, had far-reaching connections into the Maya region. The cities in Mexico. So we know that large sites like Teotihuacan and Tikal and Calakmul and Caracol, these huge Mayan sites and Mexican sites at that time were greatly affected. So we know not only locally in El Salvador where most of the people perished, but also regionally in Mesoamerica, there were huge impacts. And then looking beyond to the global impacts, we're only beginning to appreciate the impacts that this event had in far-flung places like Asia and Europe. There are historically documented instances of the dust veil and the famine that followed from Ireland, from the Roman Empire around the Mediterranean basin, from several provinces in China. So everywhere where we have good historical documentation during the 6th century records this event. And it's also seen in the archaeology, like I said, of places like Teotihuacan, but also in far-flung European environments, Scandinavia. There's a lot of research coming out of Scandinavia right now that shows that the 536 event had a pronounced impact on cultural trajectory there. So yeah, it was a global event, and the scale, we're only beginning to appreciate the scale of this eruption.
So is this the only research you're working on now, or do you have something else in the pipeline?
Well, I always have something else in the pipeline, but this is taking up quite a bit of my time right now. It's quite an exciting time to be working on the 536 event. I'm just beginning my journey into looking further, especially into the effects in the wider Mesoamerican region where I do my field research.
So this volcano, this historic volcano eruption will probably keep you busy for a little while yet.
I'm going to be busy for years working on the Ilopango eruption and its effects. And I hope many other scholars will be busy for many decades and years beyond that working on the same event.
Robert, thanks for stopping by.
Yeah, thanks, Rochelle.
You can find a link to paleoecologist Robert Dull at the link on our site at skepticallyspeaking.com. While you're there, click all the links to the myriad social media sites that will keep you up to date on show news and to iTunes so that you subscribe to the show or listen to past episodes. Thanks for listening, and see you next week.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell gonna raise a little hell, metaphorically that is. Cause we're skeptically speaking.
Skeptically Speaking is produced and distributed by Suburban Panic Media. Our guest coordinators are Rochelle Saunders and Ed Haynes. Our social media manager is Chelsea Butler. Helen Quivalon is our publications coordinator. Ryan Bromsgrove is our production manager and assistant editor. Josh Witten is our researcher. The show is edited by K.O. Myers. Our theme song was written and recorded by AOK. And I'm your host, Desiree Shell.